Hello and welcome. My name is Andrew Rams and I'm a field application scientist with PerkinElmer. In this talk, I'd like to talk about multiple strategies for improved performance of geochemical analysis by ICP-MS. There are a couple of main and common challenges in analyzing geochemical samples by ICP-MS. So these solutions are typically high in total dissolved solids. These high matrix samples can lead to plasma loading, resulting in the sample not being completely ionized in the plasma. Geochemical samples have elements of interest from the low ppb range all the way to the high ppm range, presenting a very wide range that a spectrometer would have to cover. Traditionally, these samples are analyzed twice, once on an ICP-OES for the major elements and once on an ICP-MS for the minor elements. As well, the complex nature of these samples can lead to multiple isotopic interferences that need to be removed for accurate analysis. The industry also requires long-term stability for runs with a single instrument needing to run samples of maybe 1,000 samples or more per day. I will discuss the features of the NexION series ICP-MS that make it a great instrument for geochemical analyses in the coming slides. So here's a picture of the NexION series ICP-MS. There's two main models with some minor variations between them. The NexION 1000 and the NexION 2000. Now, the NexION 2000, being a higher number, obviously must come with more features, and it does. So the main differences between the two are that the NexION 2000 comes with 3 gas lines, including one line that allows for 100% ammonia gas to be used. As well, it comes with a standard PC3 chiller to help to keep the spray chamber chilled or heated if you so choose, but normally it's chilled to help reduce oxides and to have better performance of long-term stability. So let's get back to those main challenges that face an ICP-MS when analyzing geochemical analyses. So the first topic we'll talk about is high matrix solutions leading to plasma loading. And what solutions does the NexION series offer analysts? The first way that we combat high matrix solutions with the NexION series is to use one of our 3 main systems here. We'll talk about all matrix solution. It's AMS for short. That's an argon dilution system. We also have a brand new RF generator in this series of ICP-MS. And we also have, to pair with that RF generator, a brand new LUMI coil design. So the LUMI coil is our new patented load coil. It replaces the old copper coils that are standard in most ICP-MS today. The LUMI coil is self-cooling and it provides optimal power coupling between the RF generator and the plasma. So it's designed to last, it's warranted for the life of the instrument, and it's structurally stable because of its composition. Now this is paired with a brand new RF generator. This new RF generator is a compact design. It's liquid cooled, free running, and it provides better sensitivity and more robust plasma. It actually is running at a different frequency than our previous generators were. It's now running at 34 megahertz compared to our previous 40 megahertz design. There's new onboard firmware to control the ignition, providing highly reliable, what we call fire and forget ignition, basically guaranteeing successful ignition almost every time. And the other great thing about a solid state generator is that there are no consumables to replace, no power tubes, no maintenance on the system. Now, the third option that I talked about, or the third feature that I talked about for the NexION being able to combat high total dissolved solids, so plasma cooling from this, is the PerkinElmer all-matrix solution, or AMS for short. This is a simple way to do argon gas dilution in line. So a stream of argon gas is injected into the neck of a spray chamber. This knocks out some of the droplets before they enter the plasma, thus diluting the sample. As well as diluting the sample, it has the added benefit of drying the plasma a little and increasing the ionization efficiency slightly. So the net effect is that you have more efficient ionization, fewer matrix effects, and less deposition on the interface cones. So it simplifies your sample preparation and gives you longer uptime on your instrument because there's less maintenance to the cones. The all-matrix solution is a reliable attenuation through gas dilution. We can do over 100 times dilution with this simple system, and it's a very predictable response across the mass range. So here you can see a normalized signal compared to the nebulizer gas dilution gas flows. So it is very predictable across the mass range just by balancing out the nebulizer gas flow compared to the dilution gas flow. The next challenge that's common to analyzing geochemical samples on an ICP-MS is that we are presented usually with a wide range in elemental concentrations. To help the NexION series of ICP-MS cope with these wide ranges of concentrations, they all contain something called extended dynamic range, which makes use of the quadrupole in the NexION's universal reaction cell. As you can see in the picture in the bottom left, this is the reaction cell and the quadrupole is evident. This is an electronic dilution of targeted elements whereby individual masses can be targeted with this extended dynamic range so that an attenuation can occur on that mass alone. In the bottom right-hand corner, you can see a graph showing both the original signal of a sodium signal as well as with EDR turned on with the red line showing it an attenuation of about 10 times the signal. The electronic dilution is controlled through a parameter in the syngistic software for NexION called RPA. RPA stands for rejection parameter A, and as you can see in the table on the right-hand side, as you increase the value of RPA, you dramatically increase the suppression ratio on your targeted mass. So as you increase the value of RPA, you're actually beginning to reject more ions of your targeted mass to charge ratio. So for example, in the previous test, we showed that sodium was being rejected to the tune of 10 times rejection. In that case, RPA was set to 0.1. Electronic dilution not only allows the analysis of higher concentration elements, but it also protects the detector, extending its life. So why should you use EDR? Well, it can be used to verify metal concentrations in high purity metals and concentrates. So high purity metals include high grade ore, processed solutions, finished products, etc. The other great thing about EDR is that almost every application run on a NexION ICP-MS could probably benefit from EDR primarily to protect the detector and extend the range due to the increased sensitivity of the NexION ICP-MS series. And really, there is no drawback to using EDR. It requires no gases and does not add any increased time to your acquisition time. So it is a very, very simple way to allow an extension of the dynamic range. So the next common challenge that we would see in analyzing geochemical samples is that you can often have multiple isotopic interferences for a given mass. So there are always isobaric as well as isotopic interferences on many elements. There are three key aspects of the NexION ICP-MS design that allow us to overcome and identify these interferences. Our quadrupole ion deflector, our triple cone interface, and our universal cell technology will all aid when dealing with multiple isotopic interferences on a given mass. In the coming slides, I will cover each aspect individually. First, let's talk about the unique combination of the triple cone interface and the quadrupole ion deflector. As the ion stream enters the vacuum chamber through the cones, we have 3 cones to step down the pressure more gradually than a 2-cone system. This will keep the ion stream more focused and tighter as it gets into the vacuum chamber. Once entering the quadrupole ion deflector immediately behind the triple cone interface, we begin to separate the unionized neutrals or photons from the ions of interest. The ions of interest are then bent 90 degrees. All of the unwanted material that would contribute to a background is then sucked out into the vacuum. This helps to contribute to very good stability and very low background noise, and it helps to keep the system cleaner longer because we do not have charges on our cones to extract any ions. So no charge surfaces means nothing really wanting to attract to those cones, so they're cleaner longer. The other benefit is there is no contact with the ion stream within the quadrupole ion deflector. So these surfaces do not need regular maintenance. So really there is no maintenance past the cones in the NexION ICP-MS series. The main component in the NexION series to combat interferences is the universal cell. The universal cell allows for both KED and DRC gas modes to be run to remove interferences. The NexION 2000 has 3 gas channels, allowing for multiple gases to be run to remove specific interferences. The NexION 1000 has a single gas channel that can be used for either a single gas or a mixed gas. When using a mixed gas, the gas flow as well as the electronic conditions on the cell to promote either DRC or KED interference removal can be tuned. Thus, you can have a mixed gas of helium and hydrogen and use the tuning aspects of the cell to induce either a DRC effect or a KED effect on that gas. You can use all 3 modes for data confirmation, meaning that you can run KED and DRC gases on the same analyte to see if you are getting the same signal or if there are still interferences that have not been accounted for. And the software handles mode switching automatically, meaning that you just have to enter in your method which analytes to have which gas modes, and the software will take care of everything. Mixed gas mode works in 2 ways. Obviously, a mixed gas will have a combination of 2 different gases, and in this example, we are using a mixed gas of helium and hydrogen. Helium is the common gas that will be used in KED or collision mode, and hydrogen is a gas that can be used for a DRC reaction. When tuning the cell, you can tune the cell to either create an energy barrier, thereby rejecting polyatomic interferences that have lost kinetic energy as they interact more with helium than the target analyte, thus removing the interference preferentially to your ion of interest. However, there is still a slight attenuation of your ions of interest. Whereas you can tune the cell for a DRC effect, promoting a reaction with the hydrogen reactive gas, thus removing interferences that are affected by hydrogen and giving yourself a much cleaner signal on your ion of interest. So single gas switching between collision and reaction is using a combined collision and reaction gas, and both collisions and reactions can take place in a single run, just by varying the tuning on the cell. There are benefits of this is that there are less overheads, meaning there is reduced setup time and instrument optimizations. There is no gas pressurization or venting required because we are using one gas, we are not switching gases. And you can get improved detection limits for a number of elements, including selenium. Now, the final challenge in terms of analyzing geochemical samples using an ICP-MS is long-run stability. So with so many different elements in these samples and such a wide variety of concentrations, you can often see a promotion of drift, especially if ions and elements and material is being built up on interior surfaces. However, the key concept of the NexION ICP-MS series is to promote very low backgrounds and remove all of that background very efficiently without promoting any buildup of this material on the interior of the ICP-MS. As you can see from this stability run, where we ran a continued calibration verification standard every 10 samples over a period of 13 hours without recalibration across a wide range of analytes, you can see that there is long-term stability. We only exceeded 110% or plus or minus 10% on one point. But now let's talk about some more real-world examples, especially in terms of speed and accuracy, as this is quite important in many large-scale geochemical labs. Some reaction gases are better than others for interference removal. With multiple gas channels, 100% ammonia is a good gas for removing interferences on certain elements, such as sodium, magnesium, potassium, and calcium. Both ammonia and hydrogen are equally good for removing interferences on other elements, such as manganese and iron. While in other cases, such as arsenic, hydrogen will remove the interference better than ammonia will. So as I've stated many times through this presentation, labs will often get a wide variety of samples that require different digestion methods to put them into solution. So different acid concentrations add varying amounts of interferences. So an acid digestion with hydrochloric acid will cause more chloride interferences, for example. Here we show spike recoveries across the mass range for 3 different digestion methods. We have aqua regia digestion, marked by the AQ or the blue diamonds. We have a 4-acid digest, the green squares, marked as MA, and then a lithium borate fusion, marked as the green triangles, LF. They were run using the same method with a mixed gas, in this case helium-hydrogen, in the same run, showing that recoveries are good across the mass range and preparation range. There were a couple of exceptions there, but for the most case, one gas mixture using AMS gas, EDR, and many of the different techniques that we can apply on the NexION series, we are getting very good, stable, and reliable recoveries for all of these sample types in different matrices. Here's another example of the NexION ICP-MS using a single gas to great effect. Again, in this case, we're using a gas mixture of helium and hydrogen, and we're showing you the recoveries of standard reference material SBC1. In this case, the majority of elements were recovered at 90 to 100% of the certified reference, and all elements were recovered at 80 to 100%. When you look at the bar graph, you can see that there is different color coding. The different colors indicate different modes that we're running the gas in. So the blue bars are representing low flow KED, the green bars are high flow KED, and the yellow bars are DRC, so tuning that gas to make use of the hydrogen reaction effect. As well, AMS was used, and an ESI fast system was also used. So we were trying to get high throughput in this case, meaning faster analysis, reduced maintenance, and reduced consumable costs. For comparison's sake, we would like to present data showing you the differences between a multi-gas and single gas method. The bar graph on the top shows a 3-gas method where KED was using helium gas and DRC gases of pure ammonia and pure oxygen were also utilized. In the bottom bar graph is the single gas method using a helium-hydrogen mix, and again, blue lines denoting low flow KED, green for high flow KED, and yellow for DRC. Now, the hydrogen is not as universal as using other gases, so we did not utilize as much DRC in this effect. And as well, the recoveries were better when we could tailor each individual isotope and each individual element to a different gas mode. But that being said, the single gas mode, as stated in the previous slide, was still recovering everything within the 80 to 120% recovery. And we were still getting 38 out of 40 elements measured in the multiple gas mode. So 95% of elements measured were coming back within 90 to 110%. So slightly better using 3 gases. The single gas mode is still quite usable. In conclusion, the NexION series ICP-MS does provide solutions for geochemistry analysis in multiple ways. We have the argon dilution system, the AMS, to reduce plasma loading and keep cones clean longer. We have the extended dynamic range, or EDR, to expand the range that allows both major and minor ions for analysis in a single run without having to do separate dilutions. We also have our quadrupole ion deflector and triple cone interface, QID and TCI, to reduce background interferences, keep the instrument clean, and minimize drift. The solid state generator and LumiCoil provide for increased robustness of the plasma and better ionization to help us give a better ion stream into the system. And finally, the universal cell technology is key to our interference corrections. This allows both DRC and KED operation, whether it's with a single mixed gas or with multiple gases in the same method. Thank you for your time today. I hope that this presentation was able to enlighten you in the different techniques that can be used to overcome certain interferences and certain obstacles faced by technicians analyzing geochemical samples by ICP-MS. Please feel free to contact myself or my colleagues listed below for any questions that you might have. Thank you and take care.